6:50. Someone remind me we're ending at 6:50. Hey, 2 likes already. Uh, yeah, 4 people. Some people aren't here. ठीक है. Okay. How's your understanding so far? I was looking at the videos. How was it? Did you guys understand everything? Did you guys understand how concentration affects the rate of reaction, general idea about rate of reactions, and how many of you are upset we're having a class on a public holiday? I think that's a real question. Asking the real questions. You guys are not saying anything. Aya, how are you? Atika, how are you? Can you guys hear me fine? Or maybe I think everyone's just waiting for something. Which video? The last class, yesterday's. Sir Bilal took it, na? Concentration. I'm good, Haya. Thank you for asking. You guys understood everything, right? Yeah, perfectly fine. Oh, okay, you are perfectly fine. Did you guys, Atika and Haya and Mesam, you guys understood everything so far? How concentration? Yeah, I think it was pretty good. ठीक है. Okay. And you spent a lot of time on it. That's great. ठीक है. Now we're going to understand something else, a bit about catalysts and how they'll affect it, rate of reactions. So I think I want to spend a bit of time working on catalysts. So here's my plan right now. I'll tell you guys a story. That story से हम will get a better understanding of how graphs work. ठीक है. Once we have a better understanding of how graphs work, we'll use it to understand catalysts better, if that's okay. Sounds like a plan? How many of you are okay with that? Yeah? I think my camera's too. I can't do hand gestures anymore. Okay. Let's start. ठीक है. So the story is I took a test in my class. I took a test. And this was the result. The test was ठीक है. The test was about chemistry. There was a test and this was the result. I think the graph is a little too big. The test ठीक है. And the test has zero. I'm trying to make a graph and plot the results. It's a frequency graph, right? So number of students are here on the left hand side. So some people got, and this is divided, right? 50 is somewhere here, and yeah, all the marks are here. I won't label all of them. And okay, very few people failed, right? And some people, well, very few people got very little marks. Some people got, around the 20-ish. Some people got around the 30-ish. Quite a bit got around the 50-ish. Then it was a difficult test, so this is what we end up seeing. Something like this. Absolutely clear? Makes sense? Yes? Well, not statistics, but we want to use that because statistics helps you understand deal with lots of information at the same time. And we're trying to look at lots of information at the same time, or particles. But, bear with me. So these kids, some are passing, some are failing. ठीक है. Let's say, here's my threshold. This is my passing grade. Passing grade. Those who passed after class went to a school event that was organized. There was an event at school on that day, and they enjoyed that event. ठीक है. Those who passed, they went to that event, right? People are, yay, they're happy. Those who failed had to improve their grade, and they went to remedial classes or stayed back in class and studied more. Does that make sense? We are continuing rate of reactions. We're talking about catalysts. Oh, I drew everything and it just popped up after I drew everything. ठीक है, but does this make sense? So some people went to the event and were happy. ठीक है, absolutely clear. ठीक है, brilliant. Okay. ठीक है. Now, if I want, let's say the principal said not many enough people came to the event, like we want more kids. I can do it two ways. Assuming some people really need to study, I can't cancel this session and throw everyone there. ठीक है, I'm giving an example, and just bear with me. ठीक है, I can give it two ways. I can do is I can increase everyone's grade by, let's say 10, by a factor of something, like let's say 10%, or add 10 to everyone's grade. And सारे बच्चों के grades will increase, and there will be more students on the right hand side of the graph after the passing thing, right? More students will come here. It'll rise and rise if I kept adding grades. ठीक है? So that's one way. One way is, let me write it down. One way is increase everyone's grades. Increase everyone's grades, so more people can have fun at the event or whatever it is. ठीक है. The other way is, I'm trying to be fair, right? I just don't want to take all the students here and like, oh, go ahead, right? So I'm a man of principle. ठीक है. The other way is I can lower the passing grade. I can say, hey, lower this over here to this side. Let me draw a new one. If I lower the passing grade to here, or maybe exactly on 50%, because that's normally the passing grade, right? If I make my new passing grade here, more people will pass without their marks changing, and they'll go to the event. Lowering grades would be unfair. Passing grades is 40%. Okay, different for some. When I was in school, the school was like 50% was pass or fail. I think it still is. And I don't know. E is at 40? Okay. ठीक है, but like different for different thing. I was just recollecting my Oscar. ठीक है, 50 as some people say 50. Does this make sense? Two ways to change the amount of people who pass. Do you guys understand this logic? Perfectly clear? Makes absolute sense? ठीक है. So this was my story, and we had an idea about graphs. Let's go and talk about catalysts. You guys ready? Okay, let me just bring in a picture. Like we say concentration में enough energy होनी चाहिए particles की. What energy do we talk about? The energy we're talking about is how fast the particles are moving. It's more or less their kinetic energy. Kinetic energy. At least for this example, assume it's kinetic energy if you don't agree to it. ठीक है? Kinetic energy. ठीक है? I'll put this in there. ठीक है? Or kinetic energy is the speed of a particle. So higher energy particles will have more speed or higher kinetic energy. I'm about to go there, Saad. ठीक है. Alternate pathways, not yet. I was just describing rate of reaction, how a catalyst will aid a rate of reaction. So let me bring this up. This was a really nice diagram I liked. It looks so ugly when we inverted the colors. Right? Looks so ugly otherwise. But I think you guys have seen this before. Oops. Oh, don't do that. Jesus. I think my iPad is a bit broken. I'm convinced. Okay. These are, well, bumper cars, right? Can I say at any given time, all these cars have the same speed? Is that true or no? All of them have the same speed. Is that true? Do you guys agree or disagree with this statement? Rafe on YouTube, go ahead, ask your question. Well, it's not true. Arisha, why do you say it's true? Because what's happening is some cars are, bumping into each other. At that point, their speed would be 0, or they slow down at least, right? They would be minimum. Some cars would be going really fast, about to bump into someone. So it would be really fast right before they bump. And some cars would be recovering from a bump, right? So they would have a variety of speeds, not one speed. In general, the average speed would be, yeah, you're right. Average speed would be more or less consistent. But each and every particle will have a different speed, or each and every car will have a different speed. Does that make sense? Thumbs up if you guys agree, if that makes sense. YouTube has a yes or no. I don't mean spam the like button. You guys get it, right? And just spam yes if you guys get it. Yes, thumbs in the comments. Great. Okay, you guys get it. So if I end up looking at particles, can I say all of them have the same speed at any given time? Let's say particle of a gas, they're zipping around. Do they have, I'm asking the same question. Do they have the same speed? Every particle has the exact same speed? What do you guys think? Yes or no? Saad says yes. But over here, do all the bumper cars have the same speed? Some will be slowing down because they just, recovered from a bump. Some would be 0 because they just collided. So at the moment they exactly collide, it'll be 0. And some would be going just about to collide, like, full speed. Okay, you said it for something else. Okay, Saad, forgive me. But let me ask this question again then. So these particles, will they have the same speed at any given time? All of them will have one speed? No, right? They'll have a variety of speeds. Some will be, really high, some will be really low. Or I could say they'll have a variety of energies at any given time. I can say they have this energy, and I'm generally talking about their average energy, right? I don't mean exactly at one time all of them have the same energy, right? And if I try to draw a graph of their energies, where this would be low or 0 energy, this would be high energy. Okay, this is what it would look like. Why does it peak in the middle area? It just kind of does how averages kind of work out. Some will have really fast, would be really fast, some would be really slow. But most will be somewhere in between this energy. ठीक है. Now Saad is confusing me. He's asking so many things. He's saying one-worded replies to some of my things, and when I read his statement, I'm saying something else, I think, so I get confused. But people, are you guys following this train of thought? Do you guys understand? Some will have high energy, some will have low energy. Saad, like you said no, and I'm like, does he not get this part? I'm just kind of confused, just how, like, you just said no, I'm like, oh, what? The AS organic does play the entire thing. Yeah. This is an O-level class, so. But do you guys follow? Farwa, how are you? Miral, welcome. Rahim, how you been? Do you guys understand this logic? Okay, sorry. Right. Understood, everyone gets it. Everyone gets this part? Everyone gets this part? Spam yes if you get it. I want to hear. Type in yes. Okay. So let's say there's an energy criteria. Bhai, itni energy, you have to have this much X amount of energy for a reaction to take place. Energy needed for the reaction to take place. Right? This is the energy. So all of these particles in front will go and react. All of these particles have enough energy to react. Whereas these guys over here do not have enough energy to react. So I can heat them up or something to make them react. And bear in mind, these are energies. I'll go back here. All these energies are changing at a time. So if I take the energy profile at a particular, or like their speed profile at a particular time, right? It'll be this, but that doesn't mean there will be molecules always at a low. One molecule will sometimes be really fast, but when it bumps into something, it'll be slow. Then it'll pick up speed again, and maybe it'll get hit by something else and get really high in speed, so it'll come here. So it's not like the grades where once you don't get a good grade, you don't change your grade until you take a retest. Their energies are changing, but at a single time, there will be only a certain amount of particles with enough energy to react, and the rest won't have that energy. And over time, they will slowly speed up or slow down and fall in this criteria and end up reacting. But this particular reaction will be slow, because not all particles have enough energy to react. They're colliding amongst themselves, but they're not colliding with such speed where they create bonds. Saad gets it. Saad knows where this is going. So what increasing the temperature does, if I increase the temperature, let me change my color. If I'm talking about temperature, it should be red, right? If I increase the temperature, that's like giving every student a bit of grade. That's like increasing the grade. That's like, oh, less people have 0, but more people will have a higher, something like that, right? So okay, I'm so sorry, this is a little too ugly. I was fast with it. What happened to my color? Okay. If you look at the red lines, there are more particles now compared to what they were for the white particles. And this is all the extra particles that are. So if I increase the temperature, that's how the rate is increasing, because now more particles have enough energy. Right? How many of you, this is kind of important. I want to pause. And ask everyone a question. Do you guys follow this train of thought? Farwa, Atika, Arisha, Miral, Mesam, Rahim, Haya. Are you guys following? Rida? Yes, yes, yes. No questions so far. Everyone gets it. ठीक है. So this is what increasing the temperature does. And the other way I can increase the rate of reaction is lowering my passing rate. If I lower this, more particles will have the required energy for a successful reaction, and they'll have a fun time, and less particles will be stuck in detention or remedial classes. I take classes on Fridays and Saturdays. Sir Bilal takes classes rest of the week. Faz. ठीक है. Does this make sense? Okay, everyone got it. ठीक है. This is what a catalyst does. This is how a catalyst works. A catalyst lowers the energy for a reaction to take place. This results in the rate of a reaction increasing. Say it. So this is the main point I feel is important, but the true definition of a catalyst, what you should know is, a catalyst is something that increases the rate of a reaction without taking part in a reaction. So I'll write that down as well. Catalyst increases the rate of reaction without being, did I say take part? It does take part, without being consumed in the reaction. It doesn't consume in the reaction. Technically it does take part in the reaction. So a catalyst will do that. It'll change the rate by lowering the activation energy, and it'll do it, but once it's done it, it's not in the product. ठीक है. So here are some examples for catalysts. There's a famous reaction, or there are three famous reactions which are industrially very popular. So one is nitrogen reacting with hydrogen to form ammonia, and if I balance this out, you'll have 2 over here and 3 over here, and I think it's balanced. This is known as the Haber's process. No, all catalysts will remain chemically unchanged. That's the definition of a catalyst. They don't. ठीक है. The Haber process has this catalyst, and the catalyst used over here is iron, Fe. Another catalyst for a famous reaction is for the production of sulfuric acid. Production of sulfuric acid. Sulfuric acid. Sulfuric. I think they changed it to an F. This is known as the contact process. Okay. And the catalyst for this is vanadium five oxide. And we have a third catalyst for the hydrogenation of alkenes, or the reduction or hydrogenation of alkenes. We don't know what these are, but these catalysts names are important because they keep asking you. That's it. Reduction or hydrogenation of alkenes to alkanes. Okay. And the catalyst over here is nickel. Oops. 3 catalysts. Okay, easy, straightforward. Okay, can I move on, or is that okay? Or do you guys want to wait? Catalyst names are important. Reduction or hydrogenation of alkenes. This last one you'll do in detail when you start organic chem. Okay, थोड़ा detail में you'll see exactly what it is. It's basically an alkene accepting some hydrogen, and you use nickel as its catalyst. Okay. It doesn't have a fancy name like this. Technically, this would also be called, you can call it reduction of nitrogen because it's gaining hydrogen, but this is known as the Haber process because we study a bit about it, which is that a special procedure is used to produce this reaction. So that's why you just don't react it. To get the maximum product with the least cost, you do it a special way, and that's the Haber process. I don't know, a contact process, to me it's so low-key cool. Contact process. Contact, you know, I don't know. But both are really cool names. You're right. Haber sounds like it was named after a guy. I always thought it was some guy named Haber and he invented it, you know. Contact sounds cool, like it's a contact process. Okay. This is clear? Let's move on. Contact sounds generic? Okay. Okay. I thought it was cool, man. My feelings are hurt. And I took that personally. Right. Okay. Here we have another way of looking at a catalyst. Do you guys understand gravitational potential energy? Yes, you do. Okay. So, the change in gravitational potential energy over here, if this ball is over here on the left hand side, and then it falls down over here, what is the change in gravitational energy? How much potential energy did it lose? So the height I'll use is, would it be this, h1? Would it be this, h2? Or would it be this, H3. Now we have physics. Thanks, Cheyenne, for spamming my YouTube comments. Thank you so much. You're doing God's work right there. H3 is activation energy? Absolutely. But what is the change in gravitational potential energy over here? H1? The height 1 will give you the change in potential energy? H2 minus H1? Well, isn't that just H3? Isn't this the height used to calculate potential energy? Because the ball is technically over here in height, then it's here in height. The change is H1. It's not showing on the screen, even though I've written it. I'm just waiting for it to show. Because it's going to disappear. Come on, show. Okay, there we go. Yeah, that height is H1. Okay, so H1 is the height. But you're right, that's the activation energy. So what I have to do is I have to take this ball up, all the way up here. I have to give my own energy over here, and then the ball falls down on its own accord. Over here, my activation energy is recovered. Well, I don't fully get it, but it's negated, you know, this cancels out. This change in height cancels out this change in height, but this is all the energy given out after that, right, of the ball. And this is very true for an energy profile diagram. This is literally what an energy profile diagram looks like, even though this is, and you guys could tell I was talking about an energy profile diagram where we're talking about terms like TK. I have my reactants over here. I have my products over here. Right? And when I introduce a catalyst to the same chemical reaction, what ends up happening is it lowers the activation energy. Lowers the activation energy for this chemical reaction. So if this particular height was activation energy, this height over here would be, let me bring this to the side, would be activation energy catalyst, with a catalyst. Do you guys follow? Is it necessary to study from the book? The book organizes things everywhere, it's right there. But if you don't like the book, don't look at the book. But I think most people know this part. Okay. Any questions so far? And I'm having issues because it just looks weird. And I love my camera zooming out every 2 seconds. Do you guys get this part? I wonder if Shayan's still spamming. I guess he stopped. I love how YouTube, I should stop going on YouTube at this point. I don't get any love. I get people like Cheyenne, then I'll get a dislike, which will hurt my feelings. Then we have people talking about AS chemistry. No questions, straightforward. This is easy for you. You guys get it? Catalyst is more or less done. Let's see if I have anything else written down. You guys get it? You guys understand this bit? You guys can do a question. Do you guys want me to focus on this part anymore? I know I don't think I did it enough, but you guys seem to be very confident. Should I just skip over and go to the next part? No questions? Yeah. I think he's gone now. Can I not block him from the eCam thing? I'll have to go online and block him. All right. Is he still? Okay, never mind. It's fine. I guess he really likes Sir Bilal. It's okay. It's okay. It's okay. Okay, I think people get this. No one's asking questions. Okay, let's move on. What I'm going to ask is, what we'll do right now is, catalyst is more or less done. So do you guys, so we have temperature affecting the rate of reaction, concentration affecting the rate of reaction, pressure effect for gases affecting the rate of reaction. What else is there? Temperature ho gaya, ye ho gaya, ye ho gaya. Surface area affecting the rate of reaction. That's really cool, Vasa, how surface area works. And now we have catalysts affecting rate of reactions. Okay. Now what we'll do is, we'll figure out how we end up measuring a rate of reaction. How do we measure rate of reaction? Measuring rate of reaction. Okay. I do a lot of and so Bilal keeps making fun of me for doing hms. He makes so much fun of me for doing All right. ठीक है, हाँ, I say ठीक है a lot. ठीक है, and there was another word people said, I said, yes, Sayed. All right, they got it. All right, ठीक है. So here's one way to measure the rate of reaction. Okay, I'll just continue because, you know, also I think we don't have too much time because this class ends at 3:50, 6:50, 3:50. Why am I saying that? Okay. What's going to happen is I put magnesium in here and this chemical reaction will take place. Let me write that down quickly with some nice colors. Magnesium will react with hydrochloric acid to form magnesium chloride. I guess you guys can work with this equation as well. NaCl. And I think it's balanced now. And if it's not balanced, don't add me. Right? And yeah, this is what I do. This is what I do. And what I'll do is, every minute or so, every fixed time, I'll record the reading and write it in a table. What's going to happen is, as more and more hydrogen is produced, it's going to push away the gas syringe and it moves easily without leaking any gas, and it's going to expand as more and more hydrogen is produced. And what I'll do is, periodically with a clock in front, I'll record what the volume is per time. And what I'll end up getting is something like this. Let's see if I can fit it here. I believe I can. I believe I can. I believe I can. ठीक है. What does Sir Bilal say about typical results? Okay. And this is typical results. ठीक है. That wasn't on purpose. Okay. So time in minutes, every 30 seconds, I jotted it on the table. And as soon as this time happened, I would record. So at 0 time, there was 0 volume. Then I realized it's 8, it's 14, it's 20, 25, 29, 30, so on and so forth. All right? Now, two things you can notice here right now is the reaction stops happening at a particular time. What is that time? At 5 minutes past the reaction initiation. Okay? And it stops, and how do I know it stops? Because there's no more gas being produced, so there's no change in volume of the syringe. That's one thing. He mostly says, and kind of sings. Yes, he does that. I probably caught it from him. ठीक है. I'll stop saying ठीक है. 40 is telling me no more gas is being produced. So I'm very confident the experiment stopped at 5 minutes. The other thing is, you can also tell, look how much gas was produced in the first 30 minutes, first 30 seconds. 8 centimeter cube. That's the worst 8 I've drawn. 8 was produced in the first 30 seconds. Then what was produced in the second 30 seconds, or the first minute? How much gas after that was produced? Well, isn't that going to be 14 minus 8, which is 6? Then how much? 6 again. Then how much? 5. Then 4. Then 4 again, I think. Then 3. Then 2. Then 1. Then 1 and 0, 0, 0. This is the amount of gas produced every minute or so, every 30 seconds. You notice early on, a lot of gas was produced. And after that, some little gas was produced. Volume is decreasing. Good. You guys get it? But this information is a little more better understood if you plot it as a graph. I love taking class from my home, so I have so many things to do. And I have my camera on as well. Okay. That's the same graph but drawn, the same table, same information but drawn as a graph. These are the points which we recorded. First 30 seconds it was 8, then it was I think 14, right? And then they joined the lines together. And what it's telling you are two things you can immediately again pick up from this graph is when the graph starts flatlining. The graph starts flatlining. What do I mean by flatline? It's a flat line. The graph is flatlining here. That's blue doesn't look good over here. Can yellow save us? Okay. It's flatlining over here. After this, it's completely horizontal. No more gas is being produced. Abso-freaking-lutely. Ah, good old days. He doesn't say it anymore. I'm sure he will. Okay. So the reaction stops at 5%. But how can you tell over here, without doing too much math, the rate of reaction was fast early on, and later on it slows down and goes to a stop? I like how there are more people on YouTube watching our videos from like A levels and stuff rather than O level students watching it. Just maybe YouTube is the wrong demographic for O levels. No, don't say yep to me. Are you answering my question? I'm asking, my question is, maybe you're answering something else. Okay, my question is, how can you look at the graph and go, the rate of the reaction was very fast in the beginning, and it slows down, then goes to a stop? Well, steep to flat, right? So can I say the gradient is telling me the rate of reaction? The higher the gradient, the faster the rate. The gradient in the middle is going down, then the gradient over here is almost 0, then over here the gradient is 0. Okay, so the gradient is telling me the rate of reaction. Is that clear? So if I were to calculate, if I were to ask you what is the average rate of reaction over here? Let me select this and move it a bit over here. What is the average rate of reaction? What you will say is the total volume of hydrogen produced is 40, and this was produced in 5 minutes. So you'll say the average rate of reaction would be 40 over 5, or 8 centimeter cube per minute. The average rate of reaction. But if I ask you what was the initial rate of reaction, how can I figure that out? Saad and Haya and Atika is asking a question. Ask your question again, Atika. Nazif, you're missing the Monday classes? Why? What do you mean? Okay. You're talking about the volume. Go ahead, Atika. Ask your question again because I didn't understand it when you typed. I'll wait. What the straight line is, that would be 16. Are you talking about the initial rate? So what you'll do is you'll try to the best of your ability to draw a tangent where the initial rate is. That's a horrible tangent. I think we have a jackpot. I can't move it. Drat. It's not a good tangent. It's a great tangent. Okay. Okay, not the best tangent. I need it to be steeper. That's probably good. Still not the best, but good. ठीक है. ठीक है, I'll make a tangent. I shall make a tangent and I'll figure out the gradient of that tangent. I'll use any 2 points on it to figure out. One is 0, 0. The other is, I want to pick this one, right? So this is around, I'm getting, what am I getting? 24, and the time is over here, which is 1.5. Is it 1.5 minutes? Can I say 1.5 minutes? Yeah, let's go with 1.5. Yeah, 1.5 minutes because it's gradiated like that. There are 10 between everyone. So 1.5 minutes. ठीक है. So the initial rate would be 24 over 1.5, which comes out to be what? 18? 24 divided by 1.5. 16. 16. Yes, I meant 16. 16 centimeter cube per minute. Yes, you were right. Nice. But I think my graph is a little steep. It should be slightly higher. It should be slightly tilted. So slightly higher than 16 would be, but 16 is not a bad value. I'll show you what I mean because I can see a slight, yahan pe, slight ever so slightly. But I think you'll still get 16 otherwise anyway. But hey, great. But the initial rate is 16, whereas the average rate was, this is the initial rate. ठीक है. Do you guys understand? Initial rate you can get from a tangent. And initial rate is just the rate at a particular point. What point in time? 0, when time is 0. You can be asked to calculate the rate at any point in time. So if they ask you to calculate the rate at 3 minutes, what you have to do is make a tangent at 3 minutes. Use a scale, right? And then pick the best points you can and find out the gradient. And when you do that, you'll get the rate at that point in time. Yes? Yes? Yeah, spam yes if you agree. Spam no if you don't agree. Yes, okay, Saad gets it. Okay. Miral gets it, Masam gets it. How about everyone else? Aisha, Farwa, Miral, Rida. ठीक है. Muhammad Ali, what did you enjoy when you're saying kya baat hai? Let's move on. ठीक है. So one way was collecting the volume of gas. ठीक है. I'll show you some other ways of measuring the rate of reaction, which is kind of cool. Actually, let me show you this. Maybe you guys can appreciate this. Let me show you this first. I love saying kya baat hai. It's so. Atika was a bit confused. That's okay. That's fine. Tiki, you got it now? That's great. Okay. Which, if I ask you, there was experiment A and experiment B. The only difference was one of these experiments had, let's say, a higher concentration of the solution. Okay, Saad wants to skip ahead. And one has a lower concentration of solution. Let's say it's the same. It's the graph for the same experiment which we just did, magnesium reacting with hydrochloric acid, right? So let's say the concentration, this experiment was repeated twice, one with higher concentration of hydrochloric acid, one with lower concentration of hydrochloric acid. Which graph represents the concentration with higher, the concentration of HCl being higher? B is the one with higher concentration because the initial rate is faster, and not only that, the reaction ends at a earlier time compared to A, which ends probably somewhere here. Takes twice as long. Exactly. So people are getting it. Saad got it. And Saad answered a question I never asked, but I'll ask that question. Which of the two reactions are with a catalyst? B is with a catalyst, absolutely. I do remember taking some A2 classes. I don't know if they were live though. Yeah, Arib, you're absolutely right, online. Muhammad Ali still is at Kya Baat Hai. ठीक है, this is easy. Okay, let's move on to looking at other rates of reactions. One, which is slightly obvious, and if I ask you to do it in the lab, I think after 1 hour, everyone can just come up with this experiment. If some ingredient is not producing gas, or maybe there's no good way to collect gases, here's another way of doing it. Here is another way of doing it. What am I doing? At each interval of time, I'm calculating the mass of it. What's happening is, I think over here you have calcium carbonate reacting with some acid, and you're measuring the mass that's decreased, because what's happening is the gas is being produced and is giving off. So constantly the mass is, so the faster the rate of the reaction, the faster it'll lose mass. And the slower the rate, the slower it'll lose mass. So measuring the mass and plotting it out will reflect the graph of the rate of reaction. साथ साथ क्या बात है, ठीक है. And that makes absolute sense. You know what doesn't make sense? Why have I put a cotton wool ball at the top? That makes no sense to me. Does it make any sense to you guys? To prevent acid spray, but it's also a health issue. And the other thing is, the reason why I do it is if it fizzes a lot, because calcium carbonate reacting with acids will bubble a lot of gas is produced, so it bubbles a lot. Okay. So if the acid spills out, the mass will decrease. The mass will be lowered because there's spillage. Technically, it's coming out, right? So to prevent an inaccuracy, I put a cotton wool because the acid will jump, hit the cotton wool. The cotton wool will at worst get wet, but the weight of the cotton wool will, increase, or, the entire weight of the system won't change because no acid is leaving the stand. But the gas is free to escape when it's produced. Carbon dioxide is being produced and it's free to escape, so the mass will decrease over time and no false reading. Wouldn't the cotton wool change the color at the bottom? Maybe it will, maybe it won't, but do we care? It probably won't because everything over here is probably colorless. And cotton wool is white. Acid hits it, it'll stay white. Okay. So here's another way of measuring the rate of reaction. And let's see if I have a diagram for this. Well, not really. Okay. That is straightforward. You guys get this? Yes. There are recordings for AS and A2 chemistry. Just check out the channel. There's so many playlists. There's 5 years worth of work. I'm gonna check that out. There's so much work on this. It'll take you years to process it. Okay, where's my picture? Okay. The worst way, probably the least accurate, but still works, is this way of measuring the rate of chemical reaction. This is done in labs. These are all part of your practical exams, by the way. In a particular reaction where there's a precipitate forming or there's discoloration of the solution when it reacts. So you start off with preferably something that's clear, and when the reaction takes place, let's say something is being formed where it makes the solution from transparent to opaque. So what you do is you put it on a piece of white paper and you put a big X on it. Okay. And you make sure everything else in the system is the same, right? And this is kind of dangerous, by the way, if it's an acid inside, right? And you wait for the reaction to take place until the X, you can't see the X from the solution anymore, until it turns opaque enough where the solution color is strong enough where you can't see the X anymore. As soon as that happens, you click your stopwatch. After mixing everything together, you click it, right? And you note the time. So here you will not get a graph. You have only one point where the reaction starts and where the reaction ends. Okay. So this is good for proving, let's say, does surface area affect the rate of reaction? Or how does the surface area improve the rate of reaction? So what you'll do is, in one experiment, you'll have everything constant, but you'll use, if you're using, chips or something, in one place you'll use marble chips, let's say, for instance. And then you'll repeat the experiment and you'll use powdered marble. And in one of them, the rate of reaction will come out to be different. And you'll know this because this will turn opaque a lot quicker than the other reaction. It's 7 o'clock. I think the other class might be starting. Take it, but I'll continue until Sir Bilal tells me not to. Does this make sense? Absolutely. Take it. Let me show you a few more diagrams. This is what you end up seeing. I need a faster way to copy diagrams onto my iPad. Okay. This is what you see. Everything's crystal clear. It turns opaque. The colors are inverted, so it was meant to be yellow. Okay. It gets darker and darker, and you see the X disappearing. X is gone. You note the time. You're happy. Then you repeat the experiment with something else changing, maybe the concentration or something, and you record it again, and you'll realize if this took you 5 minutes, the other reaction will probably take you 3 minutes. And you say, hey, the second reaction was way faster than the first one. But you won't get a graph this time, obviously. Okay? Okay. And just for the sake of it, just for the cake, I actually really like this experiment. I thought it was a very smart way of finding out if something is faster or slower. This is what you end up like a lateral view. Okay, makes sense? That's measuring rate of reactions. Setups. So we're talking about 3 ways of measuring rate of reaction. One was collection of gas. Second is weighing the substance. Okay. And the third is opacity. We can do it in this third way as well. This third way is the least, I wouldn't say accurate, but least detailed, least thorough. But it is a good experiment if you just want to know which experiment was faster. Okay, that's it for today. If you have questions, welcome. You can ask. I've exceeded 12 minutes now. But go ahead. If you have any questions, let me know. If you guys don't, we'll have a class tomorrow going over possibly questions. What say? Haya, Rida, Mesem? You guys are so quiet. I think so. Why not? Actually, in O levels, that's a real possibility. In A levels, no. You cannot. It's all clear. Everything straightforward. Okay? Okay, if you guys don't have any questions, I'll end the class. But I'll wait for a second if people have questions. I'm waiting for people like Atika, Arisha, saying Atika's happy, Haya. Okay. Khuda Hafiz. Okay, theek hai. Brilliant. Bye-bye, guys. Take care. Bye-bye, YouTube. Take care. Allah Hafiz.